Welcome back to Summarize Science. Have you ever tried to carry a full cup of coffee while walking quickly? It's tough not to spill. Now, imagine building a robot that can not only walk but also perform delicate tasks at the same time, like carrying a plate of snacks or wiping a window. This is one of the biggest challenges in robotics today, but a new paper introduces a groundbreaking solution. They call it SEEC, which stands for Stable End Effector Control. The core problem is that when a humanoid robot walks, its whole body moves and shakes. Even small movements at the hips can translate into large, wild oscillations at the robot's hands, as you can see in these before examples where the robot drops a chain and snacks. Previous attempts to solve this usually fell into two camps. Some used precise physics models to calculate and cancel out the shaking. But these models struggle in the real world, where things like friction throw off their perfect calculations. Other methods used AI to have the robot teach itself through trial and error. While this can work, the AI often becomes a one-trick pony, only learning to stabilize its arms for the one specific walking style it was trained with. Change the walk, and the whole system can fall apart. The SEEC framework is a clever hybrid of these two ideas. It uses a physics model to give the AI a head start, telling it the ideal way to counteract the body's motion. But the real genius is how they trained the AI. Instead of training the whole robot at once, they trained the upper body controller separately. They created a virtual perturbation generator, which is like putting the robot's torso into a powerful shake simulator, as this diagram illustrates. This generator threw all kinds of simulated walking motions at the arm controller, forcing it to learn a robust strategy to stay stable no matter what the legs were doing. And the results speak for themselves. The researchers tested their framework on a real humanoid robot, the Booster T1. Here, you can see the SEEC-controlled arm holding a flexible chain almost perfectly still while walking. Meanwhile, the standard controller causes the chain to swing wildly and eventually drop. In another test, they had the robot carry a plate of snacks. The baseline method, shown on the bottom, quickly spills the snacks due to the vibrations. But the arm using the SEEC framework keeps the plate remarkably level, successfully transporting its cargo. So, let's recap what makes this so important. The SEEC framework creates much more stable and precise control for humanoid robots that are walking and working. It does this by combining physics models with a smarter way of training an AI controller. Crucially, this new method is modular, meaning the trained arm controller can work with different walking controllers without needing to be retrained from scratch. This is a significant step towards creating robots that are not just novelties, but truly helpful assistants. Imagine robots that can safely carry supplies in a busy hospital, move packages in a warehouse, or one day even help around your home. This kind of stable loco manipulation is the key to unlocking that future. Thanks for watching Summarize Science, and we'll see you in the next one.